We're live. It's actually working. Cool. Okay. 3:29, almost spring break. 19. Okay, so a store sells trampolines. The table shows the number of trampolines sold during consecutive years. Okay. Make a scatter plot of the data and find an exponential equation to model this. Okay. Use the stat feature. So we're going to go year 1. We got 1, 2, 3, 4, 5, 6, 7. So we're going to all the way up to 96. So I might go by 5s. Let's see, 10, 20, 30, 40, 50, 60, 70. I could go by 10s. 10, 20, 30, 40, 50, 60, 70, 80, 90. I'll go by 10s. 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100, right? Okay, my scatter plot then is going to have 1 and 12 is about there, right? It's about there. And then 2 and 16, maybe about there. 3 and 25, 4 and 36, 5 and 50, 6 and 67, and 7 and 96. It definitely looks exponential, doesn't it? Definitely looks exponential. All right. So, what we've done in the past is we've had 2 points, right? And we've made the equation with 2 points. Now, here's the problem. With all of these points, it might not be a perfect fit, but that's what the calculator is going to do. We're going to put it into the stat feature, and we're going to let the calculator take care of it, and let the calculator find the best line that goes through all of them. And we've done this before, just a different feature, okay? So I'm going to go to my stat, right? Quit that, quit. So I'm going to go to stat, edit. Okay, if you have old data, then highlight your list, hit clear and down arrow. Remember how to do that? If you have old data and you want to clear out all your old data, highlight your list, hit clear, and then down arrow, okay? Okay, now let's just put these numbers in, okay? So, yeah. 1, 2, 3, 4, 5. Anybody need any help before I keep going on? I'm just on stat.
You're on stat, okay.
Stat. So again, if you need help clearing your list, let me know. You need to know how to do that. Anybody?
Wait, what?
So clearing your list. Did I clear your list? Go to stat. Edit. Good. Good. You're good. Okay. Anybody else? Anybody have it? Okay. Start putting in the numbers. Then I put in 1 through 7, which represents the years. And number. Yeah.
How do I get the little ratio of whatever the best fit is?
Oh, you've got to find it. You've got to go into.
So we'll give me the last
Yeah, catalog. I'm going to go to diagnosis. Okay. Turn diagnosis on. You got to turn it on. Okay, now try it again. Okay. Now I'm going to put in my Y values. So my Y values are trampolines. So I'm going to go 12. 16, 25, 36, 50, 67, and 96. Okay? No, I'm recording and teaching salsa. Zip it. Okay? How's everybody doing?
That's on the video.
Okay. So, now, we're going to go back to stat and we're going to calculate an answer. Does that make sense? So I'm going to go to stat again and I'm going to calculate an answer. So what I'm looking for is the exponential, right? So I'm going to go down and look for my exponential. It's on there, okay? So there's my exponential regression line. So I went all the way down to 10. 10 is my exponential regression, so enter. I'm going to calculate my answer, list 1, list 2, right? So I'm going to hit enter, okay? Now, it is y equals a times b to the x, right? That's the exponential that we've been doing. So I want my y equals a b to the x. And my calculator tells me that a is about 8.46. And it tells me my b is about a 1.42. I just rounded to the nearest hundredth. So my equation then is going to be y equals 8.46 times 1.42 to the x. Do not multiply these numbers. You guys know that. You do not multiply these numbers because you have to follow the order of operations. Yeah, Daisy?
So, yesterday, I was confused how you got that because when I did it just with the two numbers, I got y equals 36 times 1
Right.
third, 1 and a third to x power.
Yeah, so the problem is if you use just two numbers, since they don't line up perfectly, if these were perfect, you could pick two. You could pick two, but they're not lined up perfectly. They're a little bit off. I mean, it's real life, right? It's real life. So are they going to follow a perfect model? No. In fact, Caleb asked me about the test, about the R value. So my calculator didn't show me an R value. Let's find out how good it does line up. So I'm going to go to my catalog, and I'm going to go down to my diagnosis. Okay, so I'm going to go all the way down to diagnosis, and I'm going to turn it on. So I went to my catalog. And I'm going to go down all the way in my catalog to my diagnosis, okay? It's a diagnostic test to find out how good my data is, okay? I got to turn it on because it's not on in my calculator, so it's on, okay? So now I can go back and do this one again, and I'll get my R squared value, okay? So if I go to my stat again, calculate my exponential, I'm going to get an R value. So R of 0.998. So Daisy, this is going to answer your question. So my data is a good fit, but not perfect. If it was perfect, I'd have a 1, wouldn't I?
Yeah.
Right? So my R is about approximately 0.998. That's a pretty good fit, but not exact because there's a little bit of fluctuation, okay? All right, thumbs up so far? Okay, let's look at number 10, the second part. So use your model, find the sales in year 10. So let's just plug 10 in. So I'm going to go, okay, y equals 8.46 times a 1.42 to the 10th power. I'm just going to need to use my calculator to do that. Correct? I'm not going too fast, or am I? How am I doing? Okay, tell me if I get going too fast. Times a 1.42 to the power of 10, right? I get about 282 trampolines. 282 trampolines. Tramps. Okay? Now, at some point in time, realistically, it'll stop being exponential, right? I mean, at a certain point, I say, no, that's impossible, right? I mean, if it goes and we're selling more trampolines than people on the earth, that's ridiculous, right? So most of these models have a short domain. Does that make sense? A short domain? Okay, now, use your model to find, so when do the trampolines reach 200? In fact, sales reach 200. Let's change this to 2,000. No, we can do 200. We can do 200. So let's go 200 equals 8.46 times a 1.42 to the x power, okay? All right, here we go. Now, let's solve. Let's solve for it, okay? So let's divide by 8.46, divide by 8.46. I'm just going to solve. How am I doing? Am I doing okay? So I'm going to calculate 200 divided by 8.46, and I get an answer of 23.64 equals a 1.42 to the x power. Okay, now we've got to get that exponent out of there, right? So what I'm going to do is change it to logs. So if I go log of base 1.42 of 23.64 equals x. So I just transposed it from exponential form to log form. So I've got log of my base, right? Log of my base of my answer equals my exponent. And then I can use my calculator and go, okay, I can do this. So I'm going to go into my math, my log any base, right? I go 1.42 base of a 23.64. I get an answer about 9. About 9. Yeah, I got about a 9.02 or about 9 years. Okay, about year 9. Okay, does that seem pretty easy? Logarithms aren't hard. In fact, they're a lot easier than some of the other stuff we've done. Okay. All right, you ready to turn the page? Now, on the back side, we're going to see a logarithm function, okay? So what happens is a logarithm function guys watching? Exponentials go like this, right? Logarithms go like this, okay? Ton of applications to logarithm functions. When you think about any population, it grows, 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 and then it levels off. Does that make sense? A lot of things work that way, right? You know, even out in the wild, whatever populations can grow really fast, and then they tend to level off. So let's take a look at example 2. Okay, the height of a tree increases with age. So it's like, you know, it shoots up, and then it starts slowly growing at certain points, right? So we'll go age down here. And so I got to get to 14. So if I go, maybe I go by 2s. 2, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, I can go by 1s. I can go by 1s. 1, 2, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14. Sure. And then height up to 26. I'm going to check 2, 4, 6, 8, 10, 12, 14, 16. Nope. Maybe I'll go by 5s. I'll go by 5s. 10, 15, 20, 25, 30. Oh, I'm teaching. I'll have to wait. Okay. So, 1 and 5.5. About there. 14, let's see, 4. And about a 15. 6 and 19. 10 and 23. I'm teaching 12 and 25. 14 and 26. Okay, definitely looks like logarithmic function. You guys see that? Okay, you guys see a logarithmic function there? Definitely a log. Or it could be a square root graph also, but we're going to let it be a log function, okay? Now, let's go again to our stat button, all right? We're going to go to our stat, and you're going to find a y equals an ln, which is a log, correct? You can find an ln, so we're going to go to our stat. We're going to go ahead first, edit. Let's put our numbers in, clear. Let's put our numbers in. So I've got a 1, 4, 6, 10, 12, and 14. Okay, and let's put in our 5.5, 15.5, 19.75, 23, 25, and 26. Okay, got them all in. Now, it has a log button, but it's going to be a ln, which is a log, right? Natural log. Because most real-life applications are going to be a natural log function. Because things grow at a e rate, so they would grow exponentially as either e or as a natural log. Okay, so then I go to my stat button, right? Go to stat, go to calculate, and what I'm looking for is the log, right? So I'm going to go down until I find log. And there it is, ln. You guys see ln reg? So it's a natural log regression line. All right, so I want ln. I want my ln reg, okay? So push enter, go down to calculate, right? Enter, and here it is. So it comes in y equals a plus b ln of x. That's my formula, right? Right off the calculator, okay? In this case, my a is about 5.31, and my b is about a 7.82. 7.82. So I'm going to rewrite my equation as y equals a 5.31 plus a 7.82 natural log of x. Okay, there's my equation. Let me highlight that. Okay, everybody with me? My R factor is about a 0.998. That's pretty good. And it looks like a natural log function to me, okay? How am I doing? Okay, now, use your model to predict the height after 20 years. So we're just going to put 20 in for the x value. That's easy. So we're going to go, all right, y equals a 5.31 plus a 7.82 ln of 20 for 20 years, right? Okay, I can do that. Just plug it in. 5.31 plus 7.82 ln, right? Use my ln button, natural log of 20, okay? Everybody see that? There it is, my calculator.
924.39.
Yeah, I got 28.7. Okay, I got about 28.7, and that is in terms of feet, right? That's how tall my tree is, okay? After 20 years. Now, use your model to predict the age when the tree reaches 50 feet. Now, this is going to take a little bit of math. I like it. It's going to be fun, okay? So we'll put 50 in for y. So I'll go 50 equals 5.31 plus 7.82 ln of x. All right, now I'm going to go through this slowly with you so we can figure out how to solve for this, okay? You ready? I'll wait for you. Thumbs up? You guys ready for me to start solving? Okay, so minus 5.3 minus 5.3, right? So we're going to subtract 5.31. We're going to minus 5.31. So 50 minus 5.31 equals a 44.69. 44.69 is equal to a 7.82 ln of x. Okay, so far so good. That made sense. Subtract, subtract. Next step, let's divide. Okay, so next step is let's divide by 7.82, divide by 7.82. So divide by 7.82. And I get about a 5.71. And what I want to do is keep that number in my calculator for accuracy, okay? So I'm going to have about a 5.71 blah, 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 blah equals ln of x. Now, here's the trick. Let me ask you, what do you think we should do next? What do you think? Huh? Change it to? You change it to exponential. So what's my base?
E.
It's that invisible e. So I've got an invisible e here. So
wouldn't it be e to the 5.71 equals x?
awesome. Yes, it is. E to the 5.71 equals x. And for accuracy, I'm just going to go e to my answer, right, to my answer, because then I get all of those great decimals in there, right? E to my answer, and I get an answer of about 303.33. So that's in terms of years. So 303 years for my tree is that tall. And we're not going to do the journal because we've done enough of the story problems. Yeah.
How do you get the answer to zoom in as to exponential?
You click it.
It's the negative button, but.
We got to use blue.
Oh, okay.
You got it? Every thumbs up? That's not too bad, is it? I like logs. Logarithms are actually pretty darn easy. Okay.